So what we're looking at here is the end results of doing diagrams that represent the forces in play in a beam bridge. You can see here we're starting off with the free body diagram that we've used through the entire calculations, where we've calculated out the reaction vertically on the left and the reaction vertically on the right, based on the information that was available to us. As we're going down to shear force, which is the second diagram here, you've got to imagine that this is where, like a pair of scissors, it's actually going to shear, it's going to cut, and it shows us where the most vulnerable point is on this beam structure. Here, there's some things that you need to notice and to realise. Where we've got a universal load here, the universal load is a direct diagonal line from point to point. When there is a point load itself, this is a direct line down. Okay, so universal distributed load, it's a gradual step-by-step load going in a downward direction, or it might be sloped up depending on the load. And a point load is directly down. You can see here in our diagram we do have another universally distributed load, and that too travels in a downward direction. Now, to check what we're actually doing when we're doing these calculations, you need to realise that we do start at a 0 point and we also finish at a 0 point on our diagram. To do these calculations, the equation that we will be using in this case is firstly, nominating a direction, a positive direction, and it's the sum of all forces must equal 0. Sorry, the sum of all shear forces must equal 0. Coming back to the next diagram here, we have what they call a bending moments diagram. Here's some features to look out for in these diagrams. Again, it starts at a 0 point and it must end at a 0 point. So it's our starting. As we're climbing, like the universally distributed load in this case, is a curve from one point to the next. Here, where the point load is, it is a direct straight line between those points. So you can see here, this is where the universal distributed load finishes, this is where the point load is, and it's a straight line in between the two. Again here, for our next universal distributed load, again it is a curve. Okay, it's a curve there, starting off short and then dropping down there. What you need to know with this one though is the calculation for this is firstly establishing the direction for a positive bending moment, and then it's the sum of all forces. My mistake there. It's the sum of all moments. The sum of all moments must equal 0 in a bending moment diagram. So that's a quick overview. Like I said, the points, there's a few little ticks and trips with this one. But you can see that everything is in line so that everything lines up within the drawing itself. And they usually, and you'll see this in a HSC question as being represented in this way, where you've got your free body diagram. Next, directly underneath it, the shear force, and underneath that is the bending moment. And you'll be asked to draw the details in based on the free body diagram. How do we get to these points that we're looking at here? That'll be in the next video to show you how we arrive at those calculations to be able to plot these points in our diagram. So in this video here, we're just going to have a quick look at how we can calculate the shear force diagrams. So starting with the basics and moving through to demonstrate how these are actually constructed. You will need to know how to do these calculations possibly for the HSC exam. They're not difficult. Again, it's knowing what you're looking at and how it can be done. So let's just go to a new screen. Okay, so for shear force diagrams. Right, now, one thing that you can do, which I find is the best way to start calculating these out, is by breaking it down into small sections. Each time that we are drawing a point, we need to know where that point is, where it starts from and where it goes. So rather than trying to do it as one big calculation, I'm going to break it down into small little ones. So here, the first one here, we've actually got section 1. And we're going to have 4 sections to this actual drawing to pick out the points. Here I'm just going to draw it. I know I've got the pin, I've got my weight going up of 1038. I then have a weight coming down here, which is 314. And the symbol for this here is like a half arrow and a shear sign. So the calculation here is, and again, nominating the direction of the force, and it's the sum of all shear forces must equal 0 for equilibrium. And in this case here, 0 equals, 0 equals 1038 minus shear. In this case here, the shear is actually happening on the 134. Okay, so I'm not taking that into consideration. So therefore, S, because I'm moving it across, equals 1038. And that is the first point on the graph. Okay, so it starts up nice and high. Here, section 2. Again, a small drawing. I've got this. Oh, sorry, one thing I didn't mention is that I know that this distance here is 4 meters. Right, and that's where the point comes in. So we can actually, so the next point's going to be at 4 meters. Here, 1038, so that doesn't actually change. I've now can add this 314 in. And the next one here, the next point here, which is 554, is now our shear. All right, that's our shear. So here, 0 will equal 1038. Remember, it's going in a positive direction. This one here is coming down in a negative direction. 314, and then again, shear. Because we're not counting the 554, because that's where our shear line is. So the shear equals 724 in this case. So that's our next point. Our next point there, like I said, if I'm going back to my diagram, I've come up 1038. I'm now coming across, it's a universal distributed load, so I've got to correct that up. Universal distributed load is down, and that's coming to that 314 point. Well, it's actually 724. 724. Now my next point across, like this will stay constant till I get to my load. Okay, so my next load, which is section 3, again, here's my diagram, 1038. I've got my first point down here at 314, second point at 554, and then the next point that we've actually got, which is the shear, is 1099. So 0 equals positive 1038 minus 314 minus 554 minus the shear. So shear will equal, in this case, 170. Oh, did I get that right? Yep. Sorry, let me just check my math here. 1038 minus 314 minus 554 equals 170. So it's going to come down to 170. Right, so this would be our zero line. Moving across now, right? So we're getting this pattern. Universal distributed load is a slope down, an even slope, coming across to our point load, coming across to our next universal distributed load, which is now our section 4. Here we go. Again, 1038. I have 314. I have 554. I then have my 1099. And then I've got my shear load, which is at the end. 0 equals 1038. You can see the pattern here. Like I said, it's not hard math at all, but it's understanding what needs to be done. Minus shear, which equals minus 9 to 9 minus shear. Moving the shear across to this side, shear will equal minus 929. So here you can see it's going to come down this way, which is the shear before heading back to the 0. So what we actually got here, this is the minus, this is the positive within the drawing, but basically what we're looking at is where the bridge is under pressure until it gets to a breaking point below the 0 and moves across. Again, straight calculations, quite easy to do when you can see them, but again in this case here we're using a direction, like setting a positive direction. It's the sum of all forces in shear must equal 0 for equilibrium, which is the formula that we're using.